Hello and welcome. In this video, we're going to be taking a look at a fairly fundamental application of partial derivatives. If you think back to single variable calculus and the first time that we learned the derivative, one of the first applications was just finding the equation of the tangent line to a function at a given point. And in order to do that, you have to use the derivative, plug in a number to get slope. Also need to know at least what point this line has to go through, and you can put it all together and come up with the equation of the tangent line. And well, if you think now we've got partial derivatives, we're going to be doing something kind of similar. Now we could maybe scale this up to a surface in R3 if we have a function of two variables. At that point in time, we can pick a point on the surface, and going in one direction along the x direction, or going along another direction in the direction of positive y, we have these partial derivatives. And that kind of gives you the idea of maybe two tangent lines. And better than that, if you have these two different directions and two kinds of slope put together, we actually end up with a tangent plane now. So let's see if we can figure out, given a function, how do you compute the equation of the tangent plane, and what can we do with that? So let's start off with a little bit of basics about what we already know about planes in R3. There are a couple different forms for the equation that we might find useful. If we want to construct the equation of any given plane, we could always start with a normal vector n that's perpendicular to the plane. R is the position vector of any arbitrary point on the plane. That's just x comma y comma z. R naught is a specific point that we know on the plane. Some sort of position vector, let's say x naught, y naught, z naught. If you take the dot product of n dot r minus r naught, that dot product is always equal to 0 by the property that n is orthogonal to r minus r naught. Now, that is a very nice small formula that always gives you the equation of a plane. But if you actually plug in a normal vector, and let's say the normal vector has components a comma b comma c, by plugging that in and expanding out the dot product, we can get scalar form of the same plane. That will give us ax plus by plus cz. A, b, c are again just the components of that normal vector, equal to d. And for at least this video, the main purpose of showing that is knowing that a plane is a linear equation in x, y, and z. So now let's tackle the question. If we have a surface in 3 dimensions, what is the equation of the tangent plane at a specific point? Now, in this video, we're going to be looking at specifically functions. Let's let z be some sort of function f of x comma y. And in order for us to even calculate the tangent plane, we're going to have a function that's fully differentiable at some point. The partial derivative with respect to x and with respect to y must both be real numbers. If that's the case, and we have a surface that is a function, then the tangent plane is also going to be a function. Let's say that the function there is capital L of x comma y. I'm using capital L here because tangent plane is a linear equation, capital L for linearization. Now let's take a look at a picture here that might help. I've already drawn this, so I can just show you here kind of an example where we've got some kind of surface, z equals f of x comma y, and given a value for x, let's say x equals a, given a value y, let's say y equals b, that's a point at AB. The z value we get by plugging into the function, and both the red surface and the blue tangent plane pass through some common point here on both surfaces. Now, we need to make this blue plane tangent to the red surface so they have the same slopes in the x and y direction. Essentially, they have the same partial derivatives. Now keep in mind that this is a tangent plane. It goes off forever. And there's a pretty good chance that that blue tangent plane is going to intersect with the red surface somewhere else in 3 dimensions. But we're really just saying it's tangent at that one point. So it has the same slope in x and the same slope in y at that given point. So it just grazes the surface and it only touches that one point in a little local neighborhood on the surface. All right, knowing that a plane is a linear equation, that means that our function L of xy is a linear function. We could write that out as some coefficient times x plus some coefficient times y plus a constant. I'm just going to choose p, q, and r as those three constant values. Now, knowing that the blue plane is tangent to the red surface, there's a few facts that we can form in order to solve for p, q, and r. The first fact here is that the partial derivatives of the blue surface and the red surface with respect to x must be equal to each other at that given point where x equals a and y equals b. So we can write that down as L partial x at a comma b equals f partial x at a comma b. But since L is a linear function, the derivative of L with respect to x is literally just the coefficient p. So that allows us to solve for p. P is equal to the partial derivative of f with respect to x evaluated at the point a comma b. Now similarly, we know that the partial derivatives of L and f with respect to y must be equal to each other at the point a comma b, and that allows us to solve for q. That tells us that q must be equal to the partial derivative of f with respect to y, also at the point a comma b. Now it's just a matter of solving for r. And there's one other piece of information that we've already talked about, and you can see from the picture that allows us to solve for r. If we were just to plug in a and b for x and y into these two functions, they must share the same z value. We can turn that into an equation as well. L of a comma b must equal f of a comma b. If you plug a and b into our function on the left-hand side, we end up with pa plus qb plus r. If we want to solve for r, we can move a couple of these terms to the right-hand side, and at the same time, why don't we plug in the expressions that we already have found for p and for q. That gives us r is equal to f of a comma b minus a times f partial x at the point ab minus b times f partial y at the point ab. Now, all of this information for p, q, and r can now be plugged in to the function that gives us the equation of our tangent plane. It's going to be a bit of a mess, but we can plug in r, we can plug in q, and we can plug in p. Now, it's not entirely pretty, but you can see we have fx, fy's, and f's all around the right-hand side. We can tidy this up a little bit by looking for a couple common factors. There are two terms here that have f partial x's in there. If we were to factor f partial x out of those two terms, we'll end up with x minus a. Similarly, we have two terms that have f partial y, and if we were to factor f partial y out of those two terms, we'll have y minus b. And after performing a little bit of that factoring, we get the scalar form of the equation of the tangent plane. Z, or we could use function notation L of x comma y, is equal to f partial x at the point AB times x minus a, plus f partial y at the point a comma b times y minus b, plus f at the point a comma b. And of course, remember that f partial x evaluated at the point, f partial y evaluated at the point, and f evaluated at the point are just going to be numbers. They're just going to be real numbers. So you can kind of get a sense that this is very similar to kind of like an mx plus b. In fact, it's really similar to what we have as the equation of the tangent line from single variable calculus. That was f prime of a times x minus a plus f of a. You see how similar this is, right? We've got two partial derivatives though. So we take one direction, the partial derivative with respect to x, and that's multiplied by x minus a. And then we've got the partial derivative with respect to y, and that's multiplied by y minus b. And then we have f of a comma b as this additional constant to make sure that the two different surfaces, one being the red surface and one being the blue plane, both pass to the same point. Now, just like with the equation of any arbitrary plane, if we don't want to write out the full long scalar form here, we may find it could be convenient to write the same plane but in vector form. In order to do that, we have to do a little bit of tidying up first so that we can make it look like that same kind of n dot r minus r naught. Let's scrap that function notation for a moment and just write z equals. And then we can rearrange a few things. The first thing we'll do is we're just going to take the z, subtract it from both sides so we get one side equal to 0. Now, it may be a little bit more useful to put that equal to 0 on the right-hand side so it starts looking a little bit more like our n dot r minus r naught equals 0 vector form. To make it really start to stick, there's one last small change that we're going to make, and we're going to flip the signs of the last two terms here by factoring out a -1. By doing that, we end up changing the signs here so that we can get z minus f of a comma b. Now we can see that there are going to be three coefficients for these three terms. The first coefficient is just going to be f partial x at a comma b. The second term has a coefficient of f partial y at a comma b. And this third term, we have a -1. Let's put that into a vector. Then we can go ahead and use our dot product. And our other vector are going to be the remaining parts of those factors, x minus a, y minus b, and z minus f of a comma b. So that looks a lot like x minus x naught, y minus y naught, and z minus z naught, with the right-hand side equal to 0. Now, as a happy little bonus here, you can see from this equation that that also actually gives us a normal vector. The normal vector at a given point on the surface is the same as the normal vector across that whole tangent plane. And that vector, as you can see, is f partial x evaluated at the point, comma, f partial y evaluated at the point, comma, -1. And so we have the vector form of the equation of the tangent plane and this extra little bonus that the vector formed by the partial derivative of f with respect to x, partial derivative of f with respect to y, comma, -1 is a normal vector to the surface at any given point x, y. You just need to plug in a comma b and you can get the normal vector anywhere you want on the surface, assuming that it is fully differentiable at that point. All right, well, let's try an example of calculating just the equation of the tangent plane to a surface at a given point now. Let's start off with a fairly straightforward example where z is just equal to a polynomial, x cubed minus 2xy plus y squared. And let's take a look at the equation of the tangent plane at a given point 2, 3. Now luckily, this is a function, so we could write z equals f of x comma y, and that would be the function x cubed minus 2xy plus y squared. We're also going to need to know the partial derivatives with respect to x and with respect to y. We could use either notation, del z by del x, or f partial x, and similarly, del z by del y, or f partial y. We'll have to calculate these two partial derivatives first, and then we can plug the point 2, 3 into the function, as well as its first order partial derivatives. Taking a look at the partial derivative with respect to x, we're going to be treating y as a constant, and so the derivative of x cubed is going to be 3x squared. The -2 and y are both constants in this next term, just taking the partial derivative of x with respect to itself, and we get minus 2y times 1, and y squared is an entire constant term just because we're treating y as a constant here, so that has a derivative equal to 0. Now, if we're looking at the partial derivative of z with respect to y, we're going to be treating x as a constant. So this first term, x cubed, is just a constant. Its partial derivative with respect to y is 0. In the second term, -2 and x are constant multiples, and the derivative of y with respect to itself is 1. And then the partial derivative of y squared with respect to y would simply be 2y. Now, with each of those pieces of information, we can go ahead and plug in x equals 2 and y equals 3. That gives us a z value of 5. that gives us a partial derivative del z by del x equal to 6. And it gives us a partial derivative del z by del y equal to 2. And these are basically like the slopes. As x is increasing, z is increasing with a rate of change of 6 with respect to x. And as y is increasing, z is increasing with a rate of change of 2 with respect to y. At this point in time, we can choose to either use our scalar form of the tangent plane or the vector form of the tangent plane. If you want to use scalar form, then we'll just have z, or L of x comma y if you like, equals, and then we take that first slope, that would be del z by del x, which is 6, multiplied by x minus 2, which is our x coordinate, plus, and then our next sort of slope here, del z by del y, is 2. That's multiplied by y minus our y coordinate, 3, and then plus our z coordinate, which is 5. And then if we want to go ahead and expand and collect terms, we can get z equals 6x plus 2y minus 13. Alternatively, if we want to use vector form, then our normal vector is going to be f partial x, or just del z by del x, which is 6. And then we have f partial y, or del z by del y, which is 2. And the z component of our normal vector is always minus 1 for a function. Then we take the dot product of x minus x naught, y minus y naught, and z minus z naught. That dot product is equal to 0. And there's our vector form. Now, if we want to, we could expand out that dot product just to ensure that we have double checked that both of these are equivalent. We could just do 6x minus 12 plus 2y minus 6 minus z plus 5 equals 0. Move the z to the other side and start collecting like terms, and we'll have 6x plus 2y minus 13. So the two forms are equivalent, depending on which is more useful. If we want to just jump right to having that normal vector handy, 6 comma 2 comma minus 1, then vector form is certainly going to be a little more useful. But this linear equation in scalar form is also very, very useful. If you remember again from single variable calculus, as soon as we have the equation of the tangent line, there are some applications of what we can use it for that are pretty basic, pretty simple. And that is, as long as we really only change x by a small amount, going a little bit further away from where we've come up with the equation of that tangent plane, then a little bit to the left or a little bit to the right of that point, the linear function, the tangent line, is going to be very, very close to the actual function itself. Now, that also applies here too. If we have a function, in this case a multivariable function, then this linear function, which is our tangent plane, gives us a pretty good approximation of nearby points on the surface. That's called linear approximation. In linear approximation, assuming that we have a fully differentiable function at a point a comma b, then if we were to travel to a point nearby instead of at a, b, we just move slightly in one direction or another to another point x comma y that's close to a comma b, then the function evaluated at x comma y is approximately equal to L evaluated at x comma y, where L is the equation of our tangent plane. We also call this the linearization of f at the point a comma b. The function for our tangent plane is just known also as the linearization of f at that point. Probably notice here that this isn't exactly the most technical definition, just near, very close to, is not exactly a very technical definition at all. You just have to keep in mind that the farther away you go, the chances are the linear approximation gets worse. But more so than that, really also depends on the curvature of the surface. If we have a function that is very curved, that would be involving some second derivatives then you wouldn't really want to use the linearization to approximate the surface when the function itself, this surface, is very nonlinear. So, like I say, it's not exactly technical. You have some other criteria in there, but we haven't really talked about second partial derivatives very often yet. We haven't quite gotten to the concept of that curvature. So I guess we'll hold on to that for now. Let's just maybe do a basic example. Let's say we want to take that exact same function, f, and we want to approximate f of 2.1 comma 2.95. Plugging in 2 and 3 into that function we've done already, and we get 5. So we can kind of imagine if we're just going a little bit further away to 2.1, that's a pretty small change in x, and 2.95, that's a pretty small change in y. We can probably imagine that z's not going to change that much. We're probably going to be pretty close to 5. That's where we can use linearization to come up with an approximate value of f of 2.1 and 2.95 without having to actually grab a calculator. We've already got the linearization of that function at 2, 3. And before we expanded out the scalar form of the tangent plane, we had 6 times x minus 2 plus 2 times y minus 3 plus 5. Here I'm using that L of x comma y notation because that really makes the most sense when we're calling it the linearization. Now we haven't really traveled too far away from the point 2, 3, so we can imagine that f of 2.1, 2.95 is approximately equal to the value of L evaluated at that point. And we can plug in x equals 2.1 and y equals 2.95 into this linearization function. And most of this is pretty easy to calculate. 2.1 minus 2, that's a difference of 0.1. Multiply that by 6, we get 0.6. And then we have 2.95 minus 3. That difference is negative 0.05. And then we multiply that by 2, and that is minus 0.1. And then we have plus 5. We don't really need a calculator. That just equals 5.5. And we can say that f at 2.1, 2.95 is approximately 5.5. You can go ahead and try this out in Maple for yourself. Plug in 2.1 and 2.95, and are we pretty close? I think so. We're only off by a small percentage error. You can go ahead and confirm for yourself if you like. Now, another application that follows from linear approximation that I typically find might be a little bit more useful is rather than estimating the value of f at a nearby point, we might just want to approximate the change in f. Or let's say that we want to approximate the change in z given small changes in x and y. In that case, instead of using this linearization function, we use something called differential form. Now it kind of comes from linearization, so let's start there. Let's say we start off with the linearization of z equals f of x comma y at the point x naught comma y naught. I'm using that instead of a and b for the moment. And just for convenience, let's say that when you plug x naught and y naught into the function, the z value that you get, let's say, is z naught. Now, using linearization, we know that the actual value of z is approximately equal to the partial derivative of z with respect to x times x minus x naught plus the partial derivative of z with respect to y times y minus y naught plus z naught. And here, del z by del x and del z by del y are calculated at this point x naught, y naught, z naught. That's going to be our initial point. Now, from that point, we're going to travel to a new point where we have x and y hopefully being pretty close to x naught and y naught. We don't actually necessarily want to use this to approximate z. What we want to do is we want to approximate the difference between new z and old z. So we're just going to rearrange this equation slightly. The difference, z minus z naught, is going to be approximately equal to del z by del x times x minus x naught plus del z by del y times y minus y naught. And at this point in time, it might be useful to use delta z for the change in z, delta x for the change in x, and delta y for the change in y. Keep in mind that delta x, delta y, and delta z in this formula are all changes from the initial values of x0, y0, and z0. Now this is still an approximation, but as delta x and delta y get very, very small, then this approximation gets better and better. And at that point in time, we change notation. If we have delta x and delta y being very, very small, we use differentials. dx is a tiny change in x, dy is a tiny change in y, and dz is the associated tiny change in z. And delta z and dz will approximately be the same. What we have here then is the differential form of the relationship z depending on x and y. And this can be generalized to functions of as many variables as we like. If we had maybe a quantity u being dependent on n different variables, then the differential of u can be calculated by using all of the partial derivatives with respect to all of the different variables, all of those being evaluated at some initial point, and then dx1, dx2, all the way to dxn, these are the differentials in each of those variables. Those are small changes in each variable. By plugging in those small changes, as well as these partial derivatives, we can calculate a change in the quantity u. Now, maybe to get a good visualization of this, we can do kind of a geometrical interpretation of that. We can actually look at a geometry problem that would potentially benefit from the use of differentials. So let's start off with a common volume that is dependent on at least two different variables and make small changes to each of them. In this example, let's say that we've got a project here where we need to pour a bunch of concrete. What we're going to be doing with that concrete is encasing some kind of perfectly cylindrical tank. I've drawn that here. So this cylindrical tank has a length of 8 meters and a diameter of 3 meters. Now, maybe this is some sort of tank full of some kind of hazardous materials, and we're pouring concrete in there so that we have a nice enclosure of at least 5 centimeters all around the rounded surface as well as on both ends. So we're really just encasing it with concrete. Now the question here is, how much concrete are we going to need to pour? Well, it's good to have a pretty good estimate, at least, of that volume of concrete. We might not need to know the exact value because in a practical application, we're probably going to have at least some extra concrete just in case. Now this is a volume problem and it's a cylinder, so we can even at least just start off with, how do we calculate the volume of the tank right now? And that formula is just taking the area of the cross section, which is a circle, pi r squared, multiplied by the length of the cylinder. You might remember the volume of a cylinder is pi r squared h. H makes a lot of sense if this cylinder is sitting on its flat side, but of course I've drawn it to the side, so you could maybe use length here instead of height. Doesn't really matter too much, but this might be the formula that you're familiar with. Now the volume of the tank we can calculate simply by plugging in r equals 1.5 meters, making sure that we divide the 3 by 2 to get radius, and a height or length of 8 meters. So we could just calculate the volume of what's inside the tank, but that's not going to help us to get the volume of the concrete that we're pouring around the outside. Instead, maybe think about this. If we have finished pouring the concrete, then we should end up with a new cylinder that's larger than the original. Just taking the volume of the tank plus the concrete is going to also fit the same formula, V equals pi r squared h, but r is going to increase a little bit. It's going to change from 1.5 meters radius to adding an extra 5 centimeters on there. The new radius will be 1.55. And now the length of the tank, or what I've got here is height h, 8 meters. We're going to be adding 5 centimeters on one side and 5 centimeters on the other, which is an increase of 10 centimeters. So we're going to be going from 8 meters to 8.1. Well, rather than just calculating the new volume, subtracting new volume minus old volume, the difference in volume between the tank plus concrete and just the volume of the tank alone, we could call that delta V, and that will give us just the volume of concrete that we need to pour. And in differential form, that change in volume is approximately dV, and dV equals del V by del R, one of the two variables that volume is dependent on, times the differential dr, plus del V by del H, which again, because volume depends on the length or height of a cylinder, times the differential dH. Now, we've got a change in radius of 0.05 meters. We're going to make sure to convert centimeters to meters here, but be careful with dH. Since we're adding 5 centimeters on both ends, that's a change of 10 centimeters. dH is going to be 0.10 meters. Now, before we plug those numbers in, we still need these two partial derivatives. Let's take a look at the first one. Taking the partial derivative of V with respect to R, we're going to be treating H as constant. And of course, pi is also a constant multiple, so that'll give us 2 pi RH. And then we also have to calculate del V by del H. We're going to be treating R as a constant, which means pi R squared is all just a constant multiple, and we multiply by the derivative of H with respect to H, which is 1, so we just have pi R squared. Make sure that when we actually plug in R's and H's into this expression, we're going to be plugging in the radius and height or length of the original just tank that we're trying to enclose. So this change in volume is approximately equal to 2 pi times 1.5 meters times 8 meters times 0.05 meters. If you look at the units there, we get cubic meters, plus pi times 1.5 meters squared times 0.10 meters. Again, that's also going to be units of meters cubed, which hopefully should make sense because we were going to be measuring the volume here in cubic meters, and we get an approximate volume of concrete of 4.48 cubic meters. Now, of course, if I was the one actually pouring concrete, and especially if this tank had hazardous materials in it, I'm probably going to want to bring just a little extra concrete and round up. But the beauty with this is that with differentials, we have a nice convenient formula for calculating how much additional volume we need to encase a cylinder. dV is always going to be represented by the same formula, and you just need to plug in R, H, dr, and dH to calculate the additional volume that way. Now, that same kind of concept can be applied to other sorts of relationships between multiple variables. You know, we have a relationship between pressure, volume, and temperature, for instance. If you're given a pressure and a volume and a change in pressure and a change in volume, then we can estimate the change in associated temperature as well. And, well, the other thing we can use it for might not be immediately obvious, but in a lot of natural sciences, we're concerned with errors in calculation. You're trying to calculate a quantity based off of measured quantities. And even a cylinder, for instance, if you were to pick one up and try to measure its volume, that's not a trivial problem. In math, we tend to just say, here's the radius, here's the height, plug them in. But in reality, if you're trying to measure the radius or length of the cylinder, you're using a measuring device, and that will have some associated error in measurement. The absolute error is usually just going to be marked on those scientific pieces of equipment, plus or minus 0.01 units, for instance. Well, those errors are going to be what you plug in for the differentials. It's just a small change in R and a small change in H. You plug in your measured values of R and H, and what you can calculate is dV, the absolute error in volume. It's a pretty quick way to get absolute error that way. And then if you want, you can get relative error. You just have to divide by the measured volume based off of the measured radiuses and heights, and then you can turn that into a percentage if you want. So all of that can be kind of simplifying your error calculations that way. Now we're going to be doing a lot more with partial derivatives in future videos, so stay tuned. Thanks for watching, and I'll see you in the next video.